This should be the very last part of this series, since we are really reaching the end of this miscellaneous section, and afterwards it's only going to be the conclusion. So, without further ado, mining centralization. The Bitcoin mining algorithm works by having miners compute SHA-256 on slightly modified version of the block header millions of times over and over again, until eventually one node comes up with a version whose hash is less than the target, currently over 2 power 192. However, this mining algorithm is vulnerable to two forms of centralization. First, the mining ecosystem has come to be dominated by ASIC, application-specific integrated circuits, computer chips designed for and therefore thousands of times more efficient at the specific task of Bitcoin mining. This means that Bitcoin mining is no longer a highly decentralized and egalitarian pursuit, requiring millions of dollars of capital to effectively participate in. Second, most Bitcoin miners do not actually perform block validation locally. Instead, they rely on a centralized mining pool to provide the block headers. This problem is arguably worse. As of the time of this writing, the top 3 mining pools indirectly control roughly 50% of processing power in the Bitcoin network, although this is mitigated by the fact that miners can switch to other mining pool if a pool or coalition attempts a 51% attack. Before you could use a computer, CPU, to mine in the very early days. Satoshi was mining with a laptop probably. But now it's impossible. I mean, not impossible, but you have such a low chance of getting a block this way that you are more likely to earn anything if you join the mining pool. So the mining pool essentially divides the reward among all the guys who have participated in mining. There's a pretty smart algorithm for that, but that's beyond the scope of here. And they talk about ASIC. Before you could mine with CPU, then people start mining with GPU, then with FGPA, and then finally somebody put investment into using ASICs. So to develop an ASIC, it costs about $1 million US. This is not something that a common mortal can do. The current intent of Ethereum is to use a mining algorithm where miners are required to fetch random data from the state, compute some randomly selected transactions from the last n blocks in the blockchain, and return the hash of the result. This has two important benefits. First, Ethereum contracts can include any kind of computation, so an Ethereum ASIC would essentially be an ASIC for general computation, a better CPU. Second, mining requires access to the entire blockchain, forcing miners to store the entire blockchain and at least be capable of verifying every transaction. This removes the need for centralized mining pools. Although mining pools can still serve the legitimate role of evening out the randomness of reward distribution, this function can be served equally well by peer-to-peer pools with no central control. Okay. So the thing with ASIC is that they do the SHA-256 very quickly because this is a compute intensive, but the computation is very simple. It's like roughly shuffling bits around in the input and accumulating. So a single ASIC can have hundreds and hundreds of cores or semi-cores, which are all dedicated to only computing this SHA-256. This guy doesn't really require much memories, and therefore can be rather cheap to build. So if they do this thing where you have you have to execute transactions, random transactions, it's not going to be so easy. Basically, you have to build a CPU. But I'm not sure they actually did that. So let's see afterwards if they went ahead and implemented it this way. This model is untested, and there may be difficulties along the way in avoiding certain clever optimizations when using contract execution as a mining algorithm. However, one notably interesting feature of this algorithm is that it allows anyone to poison the well by introducing a large number of contracts into the blockchain specifically designed to stymie certain ASICs. The economic incentive exists for ASIC manufacturers to use such a trick to attack each other. Thus, the solution that we are developing is ultimately an adaptive economic human solution rather than a purely technical one. But I'm again not sure they really did it. Scalability. One common concern about Ethereum is the issue of scalability. Like Bitcoin, Ethereum suffers from the flaw that every transaction needs to be processed by every node in the network. With Bitcoin, the size of the current blockchain rests at about 15 gigabytes, growing by about 1 megabyte per hour. And now it's more like 250 gigabytes. If the Bitcoin network were to process visa 2000 transactions per second, it would grow by 1 megabyte per 3 seconds. Yeah, I think Bitcoin is more like 3 transactions per second these days. 1 gigabyte per hour, 1 terabyte per year. Ethereum is likely to suffer a similar growth pattern, worsened by the fact that there will be many applications on top of Ethereum blockchain instead of just a currency, as it is the case for Bitcoin, but ameliorated by the fact that Ethereum full nodes need to store just the state instead of the entire blockchain history. Okay, that remains to be seen though. The problem with such a large blockchain size is centralization risk. If the blockchain size increases to say 100 terabytes, then the likely scenario would be that only a very small number of large businesses would run full nodes, with all regular users using like SPV nodes. In such situation, there arises a potential concern that the full nodes could band together and all agree to cheat in some profitable fashion. Change the block reward, give themselves BTC. That's a 51% attack, right? Like nodes will have no way of detecting this immediately. Of course, at least one honest full node will likely exist, and after a few hours, information about the fraud would trickle out through channels like Reddit, but at this point it would be too late. It would be up to the ordinary users to organize an effort to blacklist the given blocks, a massive and likely unfeasible coordination problem on a similar scale as that of pulling a successful 51% attack. In the case of Bitcoin, this is currently a problem, but there exists a blockchain modification which will alleviate this issue. In the near term, Ethereum will use 2 additional strategies to cope with this problem. First, because of the blockchain-based mining algorithms, at least every miner will be forced to be a full node, creating a lower bound on the number of full nodes. Second, and more importantly, however, we will include an intermediate state tree root in the blockchain after processing each transaction. Even if block validation is centralized, as long as one honest verifying node exists, the centralization problem can be circumvented via a verification protocol. If a miner publishes an invalid block, that block must either be badly formed or the state Sn is incorrect. Since S0 is known to be correct, there must be some first state Si that is incorrect where Si-1 is correct. The verifying node will provide the index I along with the proof of invalidity consisting of the subset of Patricia tree nodes needing to process a blah blah blah. Nodes will be able to use those Patricia nodes to run that part of the computation and see that the SI generated does not match the SI provided. Okay, so yeah, if you include the state root, you can detect at the point it deviates if you have a guy who is correct, because the proof of validity for the Merkle tree can be turned to a proof of invalidity. Yeah, exactly like that. Another more sophisticated attack would involve the malicious miners publishing incomplete blocks, so the full information does not exist to determine whether or not blocks are valid. The solution to this is a challenge response protocol. Verification nodes issue challenges in the form of target transaction indices, and upon receiving a like node treats the block as untrusted until another node, whether the miner or other verifier, provides a subset of particular nodes as a proof of validity. I don't think this is happening actually. Alright, anyways. Conclusion. The Ethereum protocol was originally conceived as an upgraded version of a cryptocurrency, providing advanced features such as on blockchain escrow, withdrawal limits, financial contracts, gambling markets, and the like, by a highly generalized programming language. The Ethereum protocol would not support any of these applications directly, but the existence of a Turing-complete programming language means that the arbitrary contracts can theoretically be created for the transaction type or application. What is more interesting about Ethereum, however, is that Ethereum protocol moves far beyond just currency. Protocols around decentralized file storage, decentralized computation, and decentralized prediction markets, among dozens of other such concepts, have the potential to substantially increase efficiency of the computational industry and provide a massive boost to other peer-to-peer protocol by adding for the first time an economic layer. Finally, there is also a substantial array of applications that have nothing to do with money at all. The concept of arbitrary state transition function as implemented by the Ethereum protocol provides for a platform with unique potential, rather than being a closed-ended, single-purpose protocol intended for a specific array of applications. In data storage, gambling, or finance, Ethereum is open-ended by design, and we believe that it's extremely well suited to serving as a foundational layer for a very large number of both financial and non-financial protocols in years to come. Well, this is very ambitious, but it's funny that actually, even though they provide a Turing-complete machine, so essentially they say, okay, we provide all the building blocks, and it's up to you to build your whatever you want, considering that since we are Turing complete, in theory you can create anything that is can be computed by a system, by a computer. However, in practice, the vast majority of stuff is very basic these days. And it's mostly driven by the fact that the fees are very high. I mean, not very high, but the fees make executing the contracts quite expensive. Alright, so further readings. Sophisticated. Okay, that's just the notes on the stuff from above. The first one was the fact that the Bitcoin hash address is a hash of a public key, but not the public key itself. Okay. Alright, so this is referring to the stuff that we have earlier. So they mentioned the yellow paper. See the yellow paper for the Ethereum virtual machine, which is useful as a specification and as a reference for building an Ethereum client from scratch. While also there are many topics in the Ethereum wiki, such as sharding development, core development, DApp development, research, Casper, R&D, and networking protocols. Okay, so I think the next one will be starting to read the yellow paper. But we are done. So this concludes this series about the white paper, the Ethereum white paper, and we are going to look at the yellow paper next.